Hey guys, in this video we are going to talk about the fourth and final classification of intermolecular forces, the so-called London dispersion forces. So just a quick recap. Up until now we've talked about three different classifications of intermolecular forces. The first one, we did a recap of charge-charge interactions, right? And then after that, in the last two sections, we discussed this concept of a dipole-dipole interaction, where you can get, this separation or asymmetry in a charge distribution sets up what we call a dipole moment that has a positive and a negative end, and these dipole moments have a tendency to arrange themselves such that the negative of one dipole moment is close to the positive of another, and this arrangement gives rise to this attractive dipole-dipole interaction. We then saw how these attractive dipole interactions can be built upon, and you can actually get a variety of different interactions based on this dipole-dipole concept. And we saw that hydrogen bonding was actually a case where we have a dipole-dipole interaction with partial covalent character, where you actually start to see orbital overlap. And in this specific instance of a dipole-dipole interaction, where you have that partial covalent character in hydrogen bonding, gives rise to a particularly strong force, a particularly high energy intermolecular force. In this final section, we are going to again look at another variant of the dipole-dipole interaction. However, this time we're going to find that this variant of the dipole-dipole interaction actually gives rise to significantly lower interaction energies. And we're going to see why here shortly. Okay, so before we jump in here, let's go ahead and start off with a definition of the London dispersion forces. Okay, so the London dispersion forces, as I alluded to on the previous slide, it represent actually the weakest of the intermolecular forces that we're going to be talking about. And this force is the result of temporary attraction when you have two molecules or two atoms that come in close proximity to one another. And what we end up seeing is that when these atoms or molecules come in close proximity to one another, what ends up forming are so-called temporary dipole moments. You end up forming temporary dipole moments, and the London dispersion force is the attractive dipole-dipole interaction between these temporary dipole moments. So to get an idea for what I'm talking about here, I'd like to draw your attention to the little visualization here down at the bottom of the screen, where we're indicating a helium atom on the left-hand side and a helium atom on the right-hand side, with two electrons, occupying their 1s orbitals. Okay, now what I'm going to do is, as the simulation progresses, is actually move these helium atoms closer together. And what I want you guys to watch as we move those helium atoms closer together, I want you to take a close look at what happens to the electron density on each one of those atoms. Right now, before we do anything, those electrons are existing in the spherically symmetric electron distributions, namely the 1s orbital. Okay? Now, when we move those atoms closer together, that electron density shifts over. Okay? The electrons of the helium atom on the right are attracted to the nucleus on the left. So if we see that again, those electrons are coming in, and that attractive interaction here is giving rise to essentially a polarization or an asymmetry building up in that electron density around that second helium atom on the right-hand side. Now, similarly, right, if you look at the electrostatic interaction between the electrons and on the two helium atoms, we of course have a repulsive interaction occurring. And so as the electron density on the right-hand side helium is being drawn to that first helium atom nucleus, the electrons on that first helium atom nucleus are being pushed to the other side, right? And so when you look at what's happened to this electron distribution and you take into account this asymmetry, we see very clearly that what is formed here are in fact temporary dipole moments, right? And so these temporary dipole moments, just as we saw before, will interact according to dipole-dipole interactions, right? Illustrated right here in the center. So that head-to-tail lineup of these dipole moments gives rise to an attractive force. Now, the reason why this is the weakest intermolecular force is because these dipole moments are temporary. They're very small in magnitude, right? They're temporary, meaning they only come into existence when another atom or molecule is in the close proximity and gives rise to this transient distortion in that electron density. Okay, now as a result of this fact that dispersion forces are basically resulting from motion of electrons, the strength of dispersion forces are going to depend on the actual number of electrons that you have in your atoms or molecules. So simply put, the more electrons you have, the stronger your dispersion forces are going to be, right? Perhaps not surprising here, right? Furthermore, the more contact points you have, in other words, the larger the molecules, the more opportunities you're going to have for these favorable temporary dipole interactions, and the stronger those dispersion forces are going to be. Okay? So more electrons, larger molecules, you're going to be seeing larger dispersion forces. Now, in order to get this dispersion force to come about, you need to be able to distort or that electron cloud. You need to be able to make that temporary dipole moment. So the ability or the tendency of an electron distribution around an atom or molecule to be distorted is referred to as polarizability. So the more polarizable an atom or molecule, the more easily its electron density is distorted, right? And so the higher polarizability, or the more easily that electron density is distorted, the more significant, the larger those temporary dipole moments will be in magnitude, and as a result, the stronger the dispersion forces will be, right? And so using this idea of dispersion forces and these principles that we've laid out here, we can actually make sense of another part of this figure that I showed you in the previous lecture when we were looking at hydrogen bonds. So in the previous lecture, our focus was on these guys over here, where we have this strongly electronegative element, oxygen, fluorine, or nitrogen, that can give rise to these little electrostatic sandwiches that we call hydrogen bonds that have, again, this partial covalent character, particularly strong, giving rise to particularly high boiling points. Okay, so we made sense of that slide of the plot. But now, if we turn our attention over here to the right-hand portion of the plot, what we see is that as we move from left to right to these heavier elements, right, elements that are larger, have more electrons, what we end up seeing is a steady increase in boiling point. And of course, we know that that maps directly onto a steady increase in the strength of the intermolecular interactions. Now, we know already that going across this line, well, none of these guys are engaging in hydrogen bonding, right? We need this increase in boiling point, increase in strength of intermolecular interactions as we go to these heavier elements must be attributed to something else. And it is in fact the result of these dispersion forces, right? And just as we said here in these bullet points, as you go to these heavier nuclei, you have both more electrons that can engage in this polarization process and the formation of these temporary dipole moments, and we have larger molecules whose electron density, as we saw previously, exists in a larger region surrounding the nucleus. So electrons that are further away from the nucleus, they're not held quite as tightly, right? Essentially by definition, and as a result they're more easily polarized. So you have larger compounds, more electrons, more easily polarized elements, and as a result you're seeing stronger dispersion interactions, and we have our steady increase in boiling points that you can see here in our figure. Okay. Another way that we can look at this phenomena is looking at the enthalpies of vaporization in particular, a topic that we'll be talking more about later on. But if you remember back from our discussions of these changes between the liquid and gas phase, remember that enthalpy of vaporization is essentially the energy required to break apart all the bonds holding a liquid together and essentially moving it into that gas phase. And so if we look at this sequence of halogens and noble gases here, we find that as you go down the periodic table, helium, argon, xenon, right, we're seeing a steady increase in the enthalpy of vaporization, right? In other words, more energy is required to break the molecules apart. Similarly, if you go down the row of our halogens, we find the same sort of trend. We're getting heavier halogens, these diatomic F2, Cl2, Br2, I2 compounds are increasing in their enthalpy of vaporization as you increase the number of electrons and the size of the orbitals that those electrons are living in, and hence the polarizability. Okay, so our next thing then is to look a little bit closer then and rank the relative strengths of interaction for these dispersion forces relative to the other three categories that we've discussed so far. So we already know charge, those are kind of the strongest interactions up here at the top, okay? And we placed hydrogen bonding below those and dipole, below hydrogen bonding. Now, dispersion forces, because they are the weakest force, if you have a small molecule, like what you see on the screen here, like maybe one where you're looking at methane, a single carbon with 4 hydrogens, right? Small molecule. The dispersion forces holding these molecules together are going to be very small, right? And if you're looking at a variety of small molecules, it's not uncommon to find dispersion forces that are on the order of only a couple kilojoules per mole. However, if you start building up larger and larger compounds, let's say I take a string of like 3, 4, 5, 6, 8, or go all the way up to say 10 carbon atoms, put them all together, link them all together, and make a big long carbon chain like this, well, that opens up a lot more possibilities for dispersion interactions. You can get these carbon compounds kind of stacking up on one another. A lot of strong dispersion interactions can result then, because dispersion interactions are additive, right? You have a large molecule, you've got a lot of temporary dipole moments interacting with a lot of temporary dipole moments on another molecule, and they add up, and you can actually see rather large dispersion energies resulting if you have a sufficiently large compound. So if you look at the range here on the right hand side, you can actually find for large molecules dispersion energies that are up there on the order of hydrogen bond energies, right? And so stronger and stronger than your standard dipole-dipole interactions. And so what you have to do in order to be able to predict that is you have to have some sort of idea of the size, and as we'll see a little later on in our example section, also the shape of the molecules will come into play. So to see what I'm talking about here, let's consider the first rather straightforward example where we're looking at a handful of hydrocarbons. Hydrocarbons with increasingly larger numbers of carbon atoms. Ethane, 2 carbon, propane, 3, butane, 4, and pentane, 5 carbon atoms. And what I want you guys to do is rank the following compounds, this list of 4 compounds, in order of decreasing melting point, okay? So we want to start with the compound at the highest melting point and go down from there. So this would be a good time to go ahead and pause the video, give this a shot, and then we'll start back up here with the solution. Okay, so hopefully you had a chance there to work through, and you can now go ahead and check your work. So the first thing I recommend students do when you're confronted with a problem like this is to actually draw out, remind yourself, what does that compound look like? Well, in the case of ethane, it's just 2 carbon atoms, which would represent as just a simple line if we're looking at our line angle formula for these structures. Propane then would be 2 lines like that, and then we'd have something like this and something like this for ethane, propane, butane, and pentane. Okay, so obviously here, they're all hydrocarbons. And so if we go through and we list what the dominant intermolecular force is for each one of these compounds 1 through 4, it's going to be the same for all of them. The primary force at play is going to be dispersion forces, okay? There's no charges, right? There's no permanent dipole moments. There's no possibilities for hydrogen bonding. It's only dispersion that's coming into play. And so this allows us to essentially level the playing field. If it's only dispersion at play, then all we need to do is go back and look at those factors that influence the strength of those London dispersion forces. And the three things that come into play are, again, the number of electrons, right? The size of the molecule, size, shape of the molecule, and lastly, we talked about the polarizability. Well, it's all hydrocarbons, so polarizability is going to be the roughly same or similar for all of these substances. And so really what it comes down to is really size and shape. Now the shape, again, is very similar. They're all kind of extended lines. So really the only variable that we need to consider here is the essentially weight, how massive these electrons are, the number of electrons that are present in each one of these molecules. And so obviously as you go down the list here, you're seeing larger and larger compounds, and so larger compounds corresponds to stronger dispersion forces. And so the compound with the strongest dispersion force and hence highest melting point is going to be our largest compound, pentane, followed by our second largest compound, butane, followed by propane, and finally we have ethane. Okay, and so this is going to be the basic way that you go about analyzing these problems involving dispersion forces, right? It typically boils down to just figuring out which compound's the biggest. However, there can be curveballs thrown, and I want to point out where that comes in. So remember, when I told you that you have to consider both the size and the shape of the molecule, this example that I've got on the screen here is going to illustrate that point very nicely. Okay, so we already know that the strength of dispersion forces increase with the number of electrons. Okay, so the caveat here, right, is that increasing molar mass doesn't always have the predicted impact you would think on the boiling point. Okay. And to understand this, as I said, we need to be thinking about shape, the shape of the molecule and how that influences the problem. Okay, so what I'm showing you here is a space filling diagram of N-pentane on the left, which basically has a 1, 2, 3, 4, and 5 carbon atoms. Get that in there, we go. And so we've got our 5 carbon atoms here. And these 5 carbon atoms, in the case of N-pentane, are all spread out in this little, long linear extended chain form. Okay. Over here on the right-hand side, we have neopentane, also a 5 carbon structure, but now those 5 carbon atoms are arranged in a tetrahedral configuration around a central carbon atom. So we have C5H12 for both, which means the molar mass is exactly the same for both neopentane and N-pentane. And if we just go only off of the dominant intermolecular forces and molar mass, we would predict N-pentane and neopentane to have very similar boiling points and melting points. However, that's not the case. As you can see down here, the boiling point for N-pentane at 35 or a little higher than 36 degrees Celsius is significantly higher than the less than 10 degrees Celsius boiling point for neopentane. And the reason for this comes down to the shape of the molecule. If we draw out what these molecules look like, you see that the N-pentane molecules, being by virtue of being sort of set up in these extended chains, right, we basically have an improved region, improved possibilities for London dispersion forces for these transient dipole-dipole interactions, more areas for close contact. Okay? Whereas the more spherical shape of neopentane results in these balls that simply can't pack as close. There's simply not going to be as much surface area in contact over which these dispersion forces can come into play. Okay? And so the result of that is a significant lowering of the boiling point and melting point, because we've significantly lowered the London dispersion force strength by virtue of the small area of interaction. Okay, so that rounds out our discussion then of intermolecular forces. We've talked about these four forces, and the next thing on our agenda then is to be able to think about how we can look at a molecule and identify which one of these forces are at play, and then ultimately use that interaction, that strongest dominant intermolecular interaction, to predict the relative boiling points and melting points for a variety of compounds. So in the next video, we're going to look at a set of example problems doing just that.